I honestly, my first impression was, no, this doesn't work. I was like, this is vaporware. This can't be.
Make air behave the way we want it to at the molecular level. No one else does that. No one else has ever even tried.
Sunlight out here in Arizona. We got great solar and decent energy rates at night, but I'm never going to build a Bitcoin mine out here because it's too freaking hot. Hey everybody, I'm Brian Snyder. I'm the CSIO of A.R.T Digital. I'm sitting here with Monica Fogelson, butcher that, and Scott Davis from Force Physics, DCT. So looking here today to kind of talk about an interesting topic here. Heat is the enemy. So reinventing cooling for the digital age. So Monica is going to kind of be our guide through here from Force Physics. So say hi.
Hi, guys.
How's it going? And then I guess, I'm going to kick it off here. Start with some introductions.
Yeah, we've got some fun stuff to talk about today. So let's just start with some quick introductions. Scott, Brian, can you each share a bit about your background and how you got to this current role that we're in right now?
I'm Scott Davis. I'm the CEO of Force Physics. I began working on this particular cooling project just after the turn of the millennia, and starting with a research agreement with the Army Research Laboratory in Adelphi, Maryland. They funded my project because they thought that it was a very, very interesting and important piece of technology. Should it work? Well, it works. Brian?
I'm Brian Snyder. I'm a Bitcoin miner, I guess you would say, for the 10 plus years. So I'm an OG and when it comes to that. Now work as the Chief Strategy and Innovation Officer for A.R.T Digital. And we've actually been working on this technology for quite a while prior to even that. So
yeah, how did you two first cross paths?
Yeah, so at the time, we were Bitcoin mining back in 2014, and we were actually operating in a little data center. It's currently, at the time, I think it was known as Next Fort down in Chandler, Arizona, and then it eventually became H5 bottom out. But if I recall, I actually met one of your engineers, Darren, at the facility back around 2015, 2016. It was a while ago. And you guys had this crazy invention there. And I remember looking at it going, there's no way that thing works. And it was basically a server cabinet with a bunch of processors in it, pulling outside Arizona air at like 110, 115 degrees and keeping the chips cool. You know, at that time, I was running a small Bitcoin facility. We were running about 0.5 megawatt there at the facility of a bunch of S1s and like S3s. So really, really old generation stuff a long time ago. And I think it took them a while, but eventually they convinced me to come down and actually visit you guys at the lab and, actually showed me what you guys were doing there. So it was pretty interesting beginnings.
And at that H5 facility, the rack that Brian saw was 65,000 watts of heat being generated in that rack. And like he said, I think it got to 112 outside. And we were still keeping the temperature of the electronics well within their thermal envelope. So I guess Brian, he decided he better keep talking to us.
Yeah, honestly, my first impression was, no, this doesn't work. I was like, this is vaporware. This can't be. And it wasn't really until I came to your lab and started to understand the science, which is one of the reasons we're getting together here today, is to discuss this so other people, without having to have a long-form conversation, can maybe start to understand, what we're developing here.
What exactly is it that we're developing here, and what has the progress been like so far from H5 and learning about this technology to where we're sitting today?
Yeah, it's been pretty spectacular following Scott and what he's been able to accomplish and achieve. Some of the designs that we were looking at in 2016 with the blades that you guys had and the cooling systems you guys had weren't really easily adaptable to what we were trying to accomplish in the Bitcoin space. And I think and cost effective either, but the innovations that, you guys have made recently in the strides, and, we've been working in collaboration, working on some prototype projects, which we'll be talking about here today, that are really promising and very exciting for the Bitcoin space.
I think it might be helpful for our viewers/listeners to understand what it is that we've done at a high level, Brian.
Yes.
He'll keep me from being a scientist here.
Uh-oh.
I'm in check. So basically, and I'm going to hold up a prop here.
Sure.
This little string of items is really a string of microchannels. There are about over 1,000 of them in this string. And what happens is we've very simply found a way to make air behave the way we want it to at the molecular level. No one else does that. No one else has ever even tried, I think, doing that, but we do. We have about 60 patents on it, just so you know, around the world. So the idea is that we can make this air cool extremely well. What I mean by extremely well is, in the Bitcoin world, better certainly than the air-cooled Bitcoin systems that are out there, but also it's more powerful than the liquid-cooled systems that are out there.
Absolutely. And without the use of water to begin
That's
with,
right.
too. So this
That's
is
right.
just air. We're
Just
not
air.
using water to cool the airstream or anything. There's no tricks. It's just air. And we're talking hot air.
Yeah, that like we said before, 12 degrees, we've managed to cool very high power density electronics using that, including Bitcoin machines that have been in that temperature. We've cooled CPUs and other electronics. The technology isn't limited to Bitcoin. It can be used to cool any electronics. And usually I specify, Brian, actively cooled electronics. Those that are passively cooled, if you can passively cool without a fan, do it.
We're not talking high density at that point.
You're not.
No, you're not talking very hot.
No, but this is for high density electronics. And so we do use a fan, and we use these devices configured in some form factor. This is for a Bitcoin board like this one. These fit, about 16 of them fit on this board. And we can cool that board better really than the way it's designed this is a Bitmain board. This is a Bitmain Hydro Pro Plus system, S19, and we cool the electronics actually much better than the liquid cools it.
And what's great about that, and we'll put a link up here in the video as well so people can find it, but there's particularly, this is a hydro board, what Scott is actually pointing to right here. And we've modified that with the JouleForce technology with a series of these systems and run this outside in Arizona, 190-degree intake air on a hydro, and still maintain and operate that with air only. So we've removed this giant clunky hydro block system where you'd have a water loop, direct liquid to chip, replaced it with these heat sinks and a blower, and are able to achieve cooling in temperatures where in typical hydro systems, they're going to begin scaling down at about 104 is about the max you can see these hydro systems operate before they have to substantially shed a lot of the load. They just get too hot. There's not enough air exchange with the water loop to be able to keep the chips cool enough to operate. So,
Yeah. And you started off this conversation saying that heat is the enemy.
yes.
How important is it for cooling electronics for the average person to understand? How important is that?
So heat is everything when it comes to silicon and the electronics, right? And we can talk about some of those concepts as we go into, and we're seeing that now. In the Bitcoin mining space, for example, immersion mining has emerged, and the adoption of immersion miner, while it's not as popular as the hydro miners are for new builds now, immersion mining has been around in the HPC space for decades and decades, and it's never really gained traction. It's always set on the sidelines. And here comes Bitcoin miners coming and utilizing power that we've never seen before. And I'll get into that a little bit more, but you've got immersion adoption for the Bitcoin mining space at a greater rate, and then we've seen hydro adoption in the Bitcoin mining space at a greater rate than, although similar rate to what we're actually seeing in the AI inference space now. We're seeing a lot of, and that all boils down to heat. And what's happening is, quick lesson for anybody out there that's familiar with the HPC, the AI space, the Bitcoin spaces. HPC, your typical cloud, your processors will ramp up from 30%, maybe they ramp up to 60, 70%, and then they come back down, right? So you have an average workload where you're only using about 30% of your cores, your CPU at any given time. Sometimes it goes up, but it always comes down, right? It's not extended. With AI inference, what you're seeing is much greater utilization. You're seeing 80%, 90%. With machine learning, it doesn't throttle down much, and then it just ramps right back up. So you're maybe utilizing that core 70, 80% of the time, right? It's kind of like if you're driving a car and an engine and you're revving that thing and you're constantly driving as hard as you can all the time. Eventually that engine will overheat, the oil breaks down, the system breaks down. Same thing with the CPUs, which is why they're using immersion cooling, hydroblock cooling to them. Then you've got Bitcoin mining, which is ASIC, and ASIC stands for Application-Specific Integrated Chipset. Basically means that 100% of the cores or 99% of the cores, we're utilizing every single transistor on that circuit has a purpose, and it's running all the time. So when we talk about utilization, Bitcoin mining SHA-256 and ASICs, you're 100% utilized, ramped up, full speed all the time, 24/7, and it's very, very demanding. And so we're seeing in the AI space the requirement for liquid going to the chip, but we're also seeing in the Bitcoin space we have an even larger demand for a better cooling solution compared to hydro, for example, in immersion.
Hydro and immersion is kind of what's dominating the market in the Bitcoin space right now.
That's correct, yes. Immersion, not as dominant, mostly because it's difficult to work with the fluid, but we are seeing expansion of that. But very particular hydro, we're seeing massive growth. Most of the new units that are coming out with the newer density. So what happens is silicon, when they produce these, they're measured in nanometers. It's basically how close the transistors are packed together, right? And when you have transistors packed together tighter and tighter and tighter, they generate more heat in a smaller amount of space, right? And so, prime example, if you look at the S21 from Bitmain, it's the first miner that they put on there that says, hey, when it's above 90 degrees Fahrenheit for the intake air, you're going to lose hash rate. And so what that means is whenever it gets hot outside, these miners are more sensitive with the newer chips because they're creating more heat density on the silicon, and they're having to throttle back when the intake temperature goes up. So people are trying to circumvent that by going to immersion cooling or hydro cooling to try to cool the chip better. But it's a big challenge, and that's kind of the big pivot that people have been doing in our space.
Yeah, so you're saying the hash rate diminishes when it gets warmer outside. What is the hash rate? Why is that important?
Good question. So the hash rate is basically how you get, it's called proof of work in Bitcoin mining, right? And so what you mine with a miner is it's how we run the Bitcoin protocol in the network. We mine we call it mining, but it's proof of work. It's effectively an algorithm that's running on these machines 24/7, as much as we can provide power for them, that's trying to solve a calculation and sort of solve for this, what they call the magic number, the difficulty, get a number larger than the difficulty number, which rewards the Bitcoin miner. We're basically searching for a magic number to get rewarded and sign off on the transactions as a Bitcoin miner.
And right now they're leaning on liquid-based solutions to get that higher hash rate and higher performance.
Correct, yeah. An easy way to put it, more hash rate means more Bitcoin that you generate through proof of work and through the pool. So you want to provide more hash rate. The other side of it is you want very efficient hash rate, meaning the amount of energy that you put in to achieve your mining output, your hash rate output. You want to be as efficient as possible, which is why a really old Bitcoin miner, you can't run, it'll use more power and consume more electrons and power and cost you more in energy than it will produce in terms of hash rate or Bitcoin. And so there's two sides of it. The efficiency side of it, which we can talk about this later on and how this actually improves the efficiency compared to even the hydros or the immersion units, which is fantastic. But it also improves, for example, by keeping the chip cool enough, it increases the amount of hash rate that we can achieve out of the same silicon.
So it's the efficiency of the board, but I'm wondering if it's a liquid-cooled system, that has to take some power to circulate it through. Does that hurt your efficiency at all?
It's still an improvement over the large amounts of axial fans that they were using in the past. But when you have a hydro setup, you have the pumps that are running the fluid loop, right, to move the liquid through these particular boards. So this is an intake and an output over the ASICs. And so there's a fluid pump, but then also you have a big dry cooler that sits outside of the container. And that dry cooler is where all that hot fluid goes to. It gets exchanged with air and through large axial fans. So those dry coolers might be consuming anywhere from 30 to 40 kilowatts of power just to kind of keep the airflow moving over that dry cooler to cool off the water-cooled loop going into the miners.
Wow, that sounds kind of complicated. Would you remove liquid from your mining center if you could?
In a heartbeat.
Well, I guess we're in the right spot, huh?
Yeah. Liquid to the chip proposes lots of challenges. There's leakage that can occur, which can cause shorts either in the power supply or on the ASIC board itself. So if this deteriorates over time, it's also problematic in terms of the glycol loop. So if you're in a cold environment, you have to worry about the liquid freezing and your pipes bursting, especially if you shut down for any reason while it's really cold. While it's running, you're probably fine. You got enough heat, but as it cools off, it can actually freeze the pipes up if you're not running heat through it. So there's concerns around that. And again, you have a lot of individual moving pieces and points of failure in these systems. It's complex, and it'll decay over time. Liquid to chip is just really coming into the HPC space, but for a long time they've avoided that for a bunch of different reasons. I know, Scott, you guys have done some research on this more on the liquid cooled side on the HPC space. So what are some challenges that they see over on that side of the fence?
Well, actually, I'm gonna word this in a way that they've asked me to, which is I frequently get asked, so why would I use this interesting air cooling technology? What are the benefits of it? What are the advantages over, let's say, liquid cooling, which I hear in the AI space and in the Bitcoin space? So the advantages, there are really 4 fundamental advantages. 2 of them everyone gets, and 2 of them are conditional. So the first 2 advantages that everyone gets is if you're using liquid to cool, and let's say you're running your Bitcoin board exactly the way that the manufacturer says to run it, and you get your hash rate, as Brian has pointed out, which is very important, exactly the targeted hash rate that the manufacturer says you can get, that's great. Well, you can do the same thing using our very advanced air technology and get the same performance. And you go, well, what good does that do if I get the same performance? Well, it's what you don't have to do is you don't have to use liquid to get that performance. So you can go ahead and use this very advanced air technology and cool your Bitcoin boards just as well as you can with liquid. That's advantage number 1. So you don't have to pay for and maintain all of the complexity that's involved in a liquid cooling system. The second advantage that everyone gets is Brian indicated that, yes, you not only have the pump energy that is used to circulate the water through the water jacket or what cold plate or whatever you want to call this, but you also have the dry heat exchanger outside, and that uses all those 30 or 40 kilowatts of power to cool some amount of hot water or hot glycol mix. Well, that ends up being, and most Bitcoin operators, I believe, would say that they spend between 5 and 6% of their energy on cooling. Well, our technology, and that's called
if
overhead.
Not more.
Yeah, and that's called
realistically more.
But yes, but I'm being conservative. So this technology, this advanced air cooling technology, uses 2% overhead. So instead of 5 or 6 conservatively, it only uses 2%. So everybody gets that benefit. Not only can they cool the same heat load that a liquid system can cool or some kind of immersion or cold plate solution can do, but also the actual amount of energy that's used to do that cooling is significantly less. So those are the 2 that everyone gets, Brian.
Okay.
The third one is dependent upon the climate of where the Bitcoin farm is, or even an AI outpost or whatever. And what I mean by that is that if you are operating in an environment like Phoenix, where it frequently gets over 100 degrees Fahrenheit, you need a solution, or even over 90 degrees Fahrenheit for Bitcoin, you need a solution that can operate under those conditions. Well, as Brian has already said, we've operated this outdoors in
112 is what the video showed.
Fahrenheit, and the machine runs at manufacturer specification, target hash rate, target power, even though it's 112 degrees outside. No one else can do that. But again, if you are in an environment where you're in Alaska or somewhere in northern Canada or wherever it's cold, that may not be a factor for your Bitcoin operation, because you can run 24/7, 365 anyhow because it's cold.
Right.
But in those environments where it isn't, which are the Middle East and West Texas and other very popular Bitcoining locations, then what they typically do is they have to turn off their Bitcoin machines when it gets above, let's say, 90 Fahrenheit, when the machines start to be at risk or just don't function anymore or function as well anymore. So they turn them off. With this, you don't need to. So you can have 7-day a week, 365-day a year operation with the Bitcoin mine using this very advanced air cooling technology. So that's advantage number 3. Advantage number 4 is really economic based, the market, the energy market that you're in. So for example, which we haven't told you yet, but I told you that this air cooling technology cools actually better than liquid. And what I mean by that is you can take a Bitcoin board like this hydro board here, and you can operate it. We've operated it 34% above its rate that Bitmain says you can actually operate the board at. The hash rate has been increased by 34% when we run our cooling solution on it. Bitmain, it can't do that. So the hydro system is incapable of providing that kind of overclocking, but that's dependent upon your cost of power. So if you have inexpensive power, it might make a lot of sense to overclock the system, because when you overclock, you consume more electrical energy, and that electrical energy is non-linear with the number of, with your hash rate. So to a certain extent, if you're in an inexpensive market for power, it makes sense to overclock. If you're not in an inexpensive market, it might not make as much sense. Those are the 4 advantages. First 2 you get, everyone gets it. Second 2 are conditional.
Yeah, and I think an interesting point to look at when you're talking about that is sort of this idea that we put more energy into the board, but we don't necessarily get a completely correlated hash rate. And when we were doing the tests, these boards, these hydro boards, are designed to run and operate about 1,250 watts is about their standard nominal, and that's with liquid cooling from Bitmain direct, like just out the bag. When we retrofitted this system and we were running it, we were putting about 50% more power back into the circuits. We were running closer to 2,000 watts across the board, and we were getting about a 35%, 40% higher hash rate than what this system is designed to do. So it's not a one-to-one correlation, but I think that's kind of relevant to kind of going into the next step of this, which, kind of dropping into the silicon issues and what's actually going on here, because kind of need to explain this so people can understand the value proposition on what we're looking at with this technology here. And, fortunately, I've had the privilege of working with a bunch of really smart people that work in, the silicon world, from different companies, from Bitcoin mining, Bitcoin minings to processors. And one of the interesting things that occurs is actually what's happening in the silicon itself when it comes to the heat side of this. As we talked earlier, the nanometer nodes, our stuff is getting smaller and smaller and smaller. And that typically leads to better efficiency. You need less power to achieve more, basically, transactions on the silicon, to do more calculations, more processing, more power, right? But it also means that heat density is tighter. And what ends up happening a lot of times is, Bitcoin mines, when we're running out in West Texas or in Texas or a hotter environment, what ends up happening during the day is it gets hot outside. Our power utilization increases. And we're not talking, just a few kilowatts, right? If you've got a 10 megawatt facility, we might see a swing of, say, we're running at 8 megawatts when it's cool at night. And all of a sudden now we're running at close to 9.5, 10 megawatts of power. And a lot of people are like, okay, well, why is that occurring? And, the first one I hear is, well, you got more fans spinning. It's like, no, these are DC fans. There's only so much power that can go into them. We know that the DC fans on an S21 are going to pull about 120 watts, right? Once they're up at 100%, those fans can't go to 200, 300, 400 watts. It doesn't explain why I'm seeing 10, 15% more power utilization. So the question is, where's that power going and what's it doing? Right. And what's actually happening is quite fascinating, right? You've got all these, you've got the silicon, you've got a wafer, and they put all these little traces in the wafer, in the transistors, directly imprinted into the wafers, which is what's creating the gates and your calculation. But what happens is when they put the traces in, they're all copper, right? So all these little traces, your vias, everything else that's inside of this little tiny package inside of the silicon there, it's all copper and materials. And one of the fun things is, I go back to our science, so we'll do a science lesson really quick here, is what happens when materials heat up to their resistance? Got the answer to this one, Monica?
I can't imagine it's anything good.
What happens when a material heats up, like copper, is the resistance increases, right? And what that means is the current required, the amps required, in order to maintain that flow of electrons through that material, it increases, right? And so what that means is for me to maintain the frequency, which is how fast I'm basically putting this information through my transistors and through my chip, in order to maintain that frequency as my chip heats up, I have to feed more amps into it. More amps means more power. So what's actually happening is on individual ASIC level, this process is actually something well known called current leakage. And this occurs on any electronic device. It doesn't matter if it's Bitcoin mining or a computer or anything else, and it creates a cascade effect. The only way to combat that is to actually shut the cores down or reduce the frequency. So how fast my system's running. And so that's where I lose my hash rate, or that's where I lose my ability to, or I shut these things off if I can't drop that frequency down enough to actually maintain it. And it can lead to current runaways. And so that's a really important concept to understand, because most people think that the efficiency of the Bitcoin miner, you're just running more fans and you're using more cooling capacity to keep it cool. And it's like, no, you're actually losing energy through the current leakage, and your efficiency is going down on these machines because it's basically shutting off cores and it's still using more energy just to maintain that frequency because the resistance of the material has gone up. So theoretically, if I can keep these chips at their nominal energy or temperature rate, which is 75 degrees Celsius for the Bitmain chips, if I can keep it at 75 C, while it's intaking, say, 115 degree air, what you'll see is that the efficiency of the chip will remain more stable than what you see in the current conditions. If this chip goes up to 80 degrees Celsius, for example, or 85, suddenly a unit that might be consuming 3,000 watts, for example, at nominal, could jump all the way up to 3,300 or 3,400 watts. That's a 10 to 15% increase in utilization. And when you're talking about a 10 megawatt site, that could be an extra megawatt and a half. And that's a lot of money.
That's a good description, Brian. You're hired.
I have to back up for a second.
Sure.
So 112 degree air is cooling something that's 75 degrees
Celsius.
Right.
Yes. So understand.
It's a unit thing.
So that's about 185 degrees Fahrenheit, right? And so when we think about it in a data center, that's a great example and a great segue. In data center, what do they keep a data center at, right? It's about 65 to 70 degrees Fahrenheit, okay? And then these servers are sucking in that cold air. They're moving across that chip, that processor. That processor is still at 185 degrees, right? But the air that comes out the back of the server is about 100 degrees. So you get about a 10 degrees C rise as you pull air through a traditional server, and it's spec'd out to run at 70 degrees F, or intake about 78 degrees F, which is about 22 degrees C, right? But the output air only rises 10 degrees C. That's the brilliance of this technology, and I think we can talk about that a little bit, or, you know.
Yeah, I want to move over to the technology because
Yes,
this
I
just
agree.
sounds absolutely incredible. Scott, what is this technology? What's the name of it? How does it work?
Well, the name of it is a mouthful. It's called an accelerating molecular beam. And what that really means is, and I'll keep this to where it's not a science lecture, I'll keep it somewhat basic. So if you have an airplane, I'll give an example of something we're all familiar with. If you have an airplane that's coming in for a landing, you know, the airplane is moving pretty fast along in the direction of the runway, but it's moving pretty slow towards the runway, losing altitude towards it. It's supposed to sort of glide down, even though it's moving very rapidly along the runway. That's fine. Well, if it comes in at a steeper angle, it hits the runway really hard. So that's why they try and glide it down to the runway so it doesn't hit the runway hard. Well, air does the same thing. You can't see it at the molecular level because the molecules are so tiny. But what happens is those little air molecules, when you have a conventional fan and a conventional heat sink like this one, what happens is the air comes in, and at the microscopic level, what you don't see is that those air molecules are coming in at a really steep angle. They're like at a 45-degree angle to the surface of the heat sink. Even though you don't see it, that's what they're doing, and it's because of probability. There's so many molecules, they hit the average angle, which is 45 degrees. That's just the way math works. Well, in our device, we control that angle. So instead of it hitting at 45 degrees, it's more like that properly landed airplane that comes in and glides in for a landing. So the amount of energy that the air imparts on our little microchannel surfaces, because it's coming in at this gradual angle, is very small. So that air doesn't heat it doesn't heat the surface up very much, but the surface being hot, because it's taking heat from a Bitcoin board or some other piece of electronics, that heat comes up through our little microchannels and gets fed into this cold airstream. Even though it's room air, to the surface, it looks very cold. Actually, cryogenically cold, Brian.
Yeah.
So that's what's occurring is we turn room air into something different that as far as the Bitcoin device and our little microchannels are concerned, it's actually cryogenically cold, even though it started off as room air.
I think we need to dive into that explanation a little bit more there, Scott. I know before you've kind of explained, like, air itself has velocity. Like, the air in this room is moving around.
Yep.
I think it's important for people to understand, you know, the velocity aspect of that and why it's cryogenically cold to the surface.
So I'll go back to my example
Yeah.
of the airplane. Thank you, Brian. He'll keep me on track. So air in any room that's, let's say in here, it's a 25 C, room, something like that in the 70s Fahrenheit. The air in this room is moving at about 500 meters a second. And the reason is that's what the velocity of the little air molecules, the average velocity of them, is directly correlated to the temperature of the room. So at this temperature, the average air molecule is moving at 500 meters a second. So back to that 45-degree angle thing, which is your point, that if we have an air molecule that's coming in at a 45-degree angle towards a surface, like in our little Bitcoin microchannels that we have in here, these are all microchannels. If we have an air molecule that's coming in at a 45-degree angle, that's the same thing as if it's starting at 500 meters a second, at a 45-degree angle, half of its velocity is aimed towards the surface, and half of it is parallel to the surface. Now, if you change that angle, and so therefore lowering your velocity towards the surface, let's say to 100 meters a second instead of 250 meters a second. To the surface, that's cryogenically cold.
Yep. Easy way of putting it, you're kind of explaining it's like velocity is temperature and temperature is velocity. The air molecules directly correlate. If we go to absolute zero, we have zero velocity, right?
That's right.
And so with the velocities we have here, so when you're doing this adjustment, you're going to have, say, 400 or 500 meters in this direction of velocity,
That's right.
100 meters downward force. That temperature is cryogenic, where we're getting the
Cryogenically cold. That's
and that effect is what's pulling the heat out of
the hot surface.
And
That's right.
the thing that amazed me the most out of this is how hot exactly the exhaust stream is from these things. That's what impresses me, right? Go back to the data center example earlier. You got 65, 70 degree F air going in, and you got about 100 degree F air coming out. This, in my opinion, is kind of where the secret sauce of it and why I kind of thought this was crazy, right? So how you could achieve this. And this ties into efficiencies and other things we can go into later. But how would you explain, Scott, in terms of, let's a simple example, and I think we can give a couple here. What does the air look like when we bring in at 70 degree air? What's it leaving at? And what does the air look like when we bring it in at 100 or even 110 degrees air?
Oh, boy.
What does the exiting air look like?
Well, so the way we word it is that the temperature of the inlet air is whatever the temperature is. So that's just, you take a thermometer out, some kind of a temperature sensor, and you go, it's 75 or whatever it is. That's the temperature that it is when it goes in. And like you said, Brian, that velocity is about 500 meters a second. After the air molecules come into contact with our little microchannels and they extract heat from the system, because the little molecules in the, I haven't said, but in the microchannel that's in thermal contact with the board, the molecules in these little microchannels are being excited by the heat energy in that board. And so they're vibrating like crazy. And so that's why there's energy transfer, Brian, is that the molecules that are vibrating like crazy in here are hitting the air molecule harder than the air molecule is hitting them. And so that gives you a net transfer of energy to the air molecule. Now, in our system, if the board, let's say, is operating at 75 Celsius, that's its desired operated temperature. Fine. What happens is the air goes in at 75 Fahrenheit, which is 22 or whatever Celsius. But when it comes out, it's almost the same temperature as the board. So that means we're packing a lot more heat energy into a smaller volume of air. And that's where the energy efficiency comes in. So the exhaust is hot when it comes out, and I mean hot like close to 190 Fahrenheit or something like that.
Yep.
So it's very hot. It's very, very close to the temperature of the board. Now, some people, and it's beyond the scope of this podcast, but some people go, gee, if you have air that hot, you might be able to repurpose it and get energy, use that energy, because it's hot enough to do something with it, and that's exactly right.
You can certainly dry some. I've been always wanting to dry some beef jerky with it. At the Bitcoin mine,
Everyone
we have Bitcoin beef
everyone
jerky.
has their thing.
Everybody's got their thing, right? So, but I think that's one of the biggest distinctions. And an example we were talking about, we get the 75 degree Fahrenheit air coming in, or let's say 22, 24 C. But we're getting, say, like 80, 82 C out of a chip that's sitting at like 85 C, or 72 C out of a chip that's sitting at 75 C. There's never a perfect efficiency, but we're getting such a high pull through. Now, explain to me, as the temperature changes, right? Like what's happening differently between if I'm running an intake air of, say, 100 degrees F or 35, 40 degrees C, as opposed to, let's say, a cooler air like 20 C. What's the difference in the device? Let's kind of talk a little bit about, the efficiency advantages and things like basically energy, how much we need in terms of the blower or the overhead, and kind of talk about that for a minute here.
So as I indicated just before, that 100 degree Fahrenheit air that's coming in is 100 degrees Fahrenheit if you take a thermometer and measure it in the room. But once that those air molecules align and come into that grazing or shallow angle, like the landing airplane, again, that air does not look like 100 Fahrenheit air to the microchannel. It looks like cryogenically cold air. So that's step one. Step two, the energy efficiency, because it uses so little air to remove the heat, the energy efficiency, as I indicated, really, I think at the beginning of this podcast, maybe 2% overhead for cooling energy instead of 5 or 6, or Brian will probably tell you it's closer to 10. But you know, in this, using this technology, it's only consumes 2% of the power of the Bitcoin machine.
Yeah, and that's a huge thing for people to understand. Like for example, if you guys are looking at a standard S19 or an XP or an S21, and you see the big 4 fans that they've got sitting on there, that those fans will pull up to 150 watts. Just those 4 fans, right? And you factor the miner itself is running between 3,000 and 3,300 watts. It's like, okay, you know, you've got a couple percentage points, essentially the same percentage we're talking about, just the machine's fans, and that doesn't include any system fans or overhead on top of that, right? I mean, we're running on typical container in our setups in Texas, we've got another 200,000 CFM per megawatt of exhaust fans that are sitting there, right? And you're talking an additional 20, 30, 40 kilowatts of utilization plus the 30 or 40 kilowatts that exists on the miners themselves. So it's like you're already up at 6, 7, 8% overhead, possibly more when you're factoring in just everything else. And the other big thing too comes back to current leakage is how well can you keep that silicon cool? And what we've seen from the design standpoint is these Bitcoin miners where the temperature is 75 C as our target, that normally only really occurs when the outside conditions are perfect. When it's, say, 65 degrees Fahrenheit outside, sure, we can achieve the efficiency that the S21 and the S19 advertise. But as soon as that temperature creeps up, starts getting to even 80 degrees or 85 degrees Fahrenheit, we start seeing that current leakage effect because those chips are going, well, we're not really 70, 75. We're more like 77, 78 degrees. And we need a little bit more amperage here to keep ourselves going. And they start, you know, oh, resistance is increased. We need a little bit more and a little bit more. And then by the time you're up to 90 degrees, 100 degrees, it's like you're using a lot more power and you're losing hash rate because it's like, no, I got to turn some cores off. I got to shut some of these chips down so I don't overheat, or I got to lower the frequency and lower my output so that I can maintain and keep running through this heat. And so this technology on the flip side, you know, in terms of the fan and the fan curve, it's just, we just need to move, basically, as I understand, we just need to move more air through the device, through this guy, to remove that excess heat and to maintain chip temperatures where we want them to be.
That's right.
So,
That's right. That's exactly right.
Yeah.
Would it be worth it, Brian, to talk about the future a bit?
Yeah.
So I think that we've probably educated our audience as to the importance of heat and the removal of the heat, and that there are different mechanisms. There are, you know, liquid and conventional air cooling, and then this very advanced, I'll say it again, accelerating molecular beam cooling.
It's a mouthful.
It is a mouthful. So those are the 3 methods. So as far as looking forward, Brian, where do you see this going? The melding of the crypto technology, if you wish, with this advanced air cooling technology? Is that a fair question?
Yeah, that's a fair question, right? And that's exactly what we've been playing around and doing, right? What we've done so far is we've taken, for example, some of these boards, these boards that are designed for air from different types of Bitcoin miners, you know, from Bitcoin miners to hydro miners, and we've found a way to adapt this technology to fit and work on these technology-based platforms. And there's challenges with that, right? And we've been developing this for years. Scott and his team has been fantastic, but there's a lot of challenges. And what it comes down to is you can vastly see the difference here. This heatsink that's designed for this is very different than this heatsink here. And so what it means is we have to kind of come up with these elaborate structures and systems to conform these this technology to fit on existing technologies. Like, for example, if I were to build a hydro board for this unit or hydro plate for this unit, it's not efficient. If you look at the hydro plate here, the chips are more packed together. And that's more efficient for the hydro plate and the water block by doing it in this configuration. This configuration is designed to spread the chips out so that as the airflow comes in here, it's more densely packed towards the beginning of the board, and then least densely packed as the air heats up across the heatsink as it exits through the miner. And that's all in an effort to keep the cooling universal and consistent across all the chips. What's great about the way this technology works, and something that I don't think we talk about much, but it's similar to how they've designed this chip, where because of the liquid, they can more universally pull the heat off of the board effectively. This technology does the same thing, but with air. That's what's really exciting here. So when you look at the future, it's time to basically, we've already proven that this technology works with Bitcoin miners, with ASICs. We know it can compete and outperform hydro systems, right? So the next system to do is actually to design PCB boards around this technology, right? We're not reinventing the ASIC. We're not reinventing the wheel or getting into the silicon. We're simply saying we want to, just like the hydros did from the air-based units, we simply are ready to start redesigning boards using this technology and extracting the heat out more efficiently, which will bring down the costs of doing so. And ultimately, when you look at the efficiencies in terms of energy utilization, like we're talking about the dry coolers and stuff, long term will reduce costs for these systems, increase hash rate output, and decrease maintenance issues. One of the big challenges we have, you've got these liquid systems, hydro block systems, where you're constantly having to monitor the water chemistry and everything else to make sure that it doesn't it doesn't corrode and eat up the plate and then destroy your tens of thousands of dollars of equipment or more. Whereas with these systems there, it's like you don't have to worry about the corrosion, and we're not introducing water at any point in this. That's a huge point that I don't think people realize. A challenge on that is the amount of water that you need to, for example, evaporatively cool or use a wet wall. Two major issues. One, there's a cost of the water, and you're limited to the water. And it might be from a well, so it's unlimited, but then you have to treat the water. So there's a lot more to just getting water to a site than people even realize in the infrastructure. And at the end of the day, I'm introducing moisture to the electronics, to the boards. And that over time causes circuit failures. It causes, trace issues, and it'll just burn my boards out. Introducing water is detrimental to the boards. Hydros are a little bit different. But again, you still have to be monitoring that water and maintaining the water, and you've got pumps and a dry cooler and a much more complex system, where what we're talking about here is a series of these boards using modified heat sinks or using these type of heat sinks, which can all run on a single blower, right? And some of the prototypes we were envisioning and working on or thinking about here, we're looking at an entire 1 megawatt system running off of a single blower. But theoretically, we could run a 100 megawatt system or a 20 megawatt system off of a large enough blower, as long as we can achieve pressure on it. So when we look forward thinking, this scales industrially at a very, very effective rate compared to some of these other systems with far less moving parts. So like we talked about, maintenance simplifications, right? I mean, an industrial blower that would be utilized in a system like this, very good uptime, very low failure rate, right? Like I certainly can tell you, after spending some time working on these miners for the past 10 years, I've probably replaced more than 10,000 fans. Little screw gun, 4 screws at a time, the fans die. So just from a maintenance perspective, changing out fans constantly, dealing with that, it's a pain, right? Fans are a big part that this eliminates. Having a single industrial blower, probably maintenance it once every 5-10 years or something like that. It's just like a pump. They just run and they run and they run, right? So that's a huge impact on infrastructure. It also means a lot more sound abatement. Let's talk about the amount of air that we actually are using. And this plays into the efficiency of the blower versus an axial fan. I was talking earlier about my sites where I'm saying at a megawatt, I've got about 200,000 300,000 CFM per megawatt of airflow. How much air does this system use to dissipate, say, a similar and equivalent
I'm
amount
glad you asked because he thinks I don't know the answer to this. So
Well, I know you do.
Here it goes. So if you take a look, if you were to ask AI what the amount of air that's required to cool 100 watts in a conventional data center. So let's use that. It uses 9 cubic feet a minute to cool 100 watts. We use about a tenth of a cubic foot a minute to cool 100 watts. So the amount of air is very low that we use. And because of that, we don't have to push that air around with fans. So the smaller amount of air, the more energy efficient the system because you don't have to move it. So there's your answer. Is that about right, Monica? Did I get the number right?
That sounds about right.
Okay, because we just did that.
Yeah, no, this is really exciting. I can totally see how these two companies would work so well together. Brian, what are you most excited for, pursuing using this technology in your centers?
Yeah, I mean, by the time this podcast's out, hopefully we'll have some other exciting announcements, which kind of explains, the vision moving forward on that. What I can tell you is, we're pursuing, basically taking it to the next step, getting these PCBs customized and building a system around this technology when it comes to cooling and doing it properly so we can get all the numbers flushed out. But, that energy savings alone by using that much less air is tremendous, right? That's directly correlating to the energy savings of axial fans, exhaust fans, or dry cooler systems, right?
Yep.
That's huge. That's our savings. And also another thing for any site operators out there is noise. You get these fans, everything else, you've got 80, 85 decibels at 100, 150 feet, which residents don't like if they're nearby. I don't know exactly what the stats would be on a blower, but assuming the blower is internal to the container and you don't have just two open walls on the container, you actually are directing airflow. I would say
it's very quiet.
Quiet.
We run one. I think you've seen one. We run a blower in downtown Phoenix, Arizona, again, 7 days a week, 365 days a year, 24 hours a day. And that blower is barely audible when you're standing next to it in its little container with all of the electronics in it. You really can't hear it. So it is a lot quieter, Brian. You are correct.
And that's a huge benefit to us. A lot of people talk about how, hydro and immersion are quieter, and they might be quieter in terms of certain frequencies of generation sound. But when you've got those larger axial fans that are on the dry coolers, those are still generating 75, 80 decibels potentially when they're ramped up at high speed during a hotter period. And so that's a huge benefit that we're looking for from the infrastructure side of things as well. And again, the simplicity of this. I'm not attaching a dry cooler. I'm not requiring a plumber to go out there and connect, pipes, because you've got the container itself with all the hydro units. Then you have a separate outside dry cooler that attaches to it. You still have to put that infrastructure and connect everything together. It's not all in one. It still has to be assembled, where this system can be an all assembled system when we're forward looking at what this product can be in the future, right? Obviously, we've got some tests and we've got some systems to come up with finalized designs of how we want to configure the boards, how we want to extract heat from the systems, particular, and how that looks like at a scaled up process. But the nice thing is, when you look at how this scales, in a lot of ways compared to plumbing fittings and pipes and things like that, it's a much simpler methodology for ducting air.
You know what? I'm going to mention something I didn't mention before in our rehearsal for this. So each one of these little micro channels, I'm hoping that you guys can see it. Each one of these little micro channels works independently of all of the other micro channels. So if you lose a micro channel, or if you lose 10 micro channels, you still have all the rest of them, and they all still perform like they did before. So they're not dependent upon one another. I get asked that quite a bit, Brian.
Really?
It's like, well, if something happens to this, will the whole thing die? No, something would have to happen to the whole cooling system, and then you would have an issue. But if you ended up just having a tenth of these micro channels become ineffective for whatever reason,
Clogged or
whatever, then you would have a a net 10% reduction in the cooling, and that's it. It's only because each of the microchannels supports itself independently. They all function independent of one another.
I can't imagine that liquid cooling systems would operate the same way. I feel like if you have a slight issue with one of them, they're all down. Am I right in that thinking, Brian?
Yeah, I mean, there's some redundancy, and not even, I shouldn't even say redundancy. There's some split up. Like, they'll have a couple of pumps working on a system, but it's like you lose a pump, you lose a quarter of the container, right? Versus here, it's like you're still tied with your blower, but again, your blower's not going to go down. And any amount of jamming in the microchannel, it's like it would take a catastrophic amount to impact the cooling. But that's where the safeguards, I mean, if you look at any of these machines, they're monitoring the temperature of the chips. The chips get too hot, they scale them back or they shut them down.
Well,
so that's
and actually with these, Brian, just like in a personal computer or a server architecture, the blower is tied into the management chip that's looking at the temperature of the chips here. So let's say you did have a blockage of 10% of these. What would happen is that if the chips started to warm up and they got past the temperature target that you had established for it, the fan speeds up a little bit. The blower speeds up a tiny, tiny amount to make up for the difference, and you would see no difference in the performance of the board. You would have nothing that actually goes down. And because Brian will laugh, but we really put twice as many of these on there as we need, Brian.
Yeah.
And that gives you that bandwidth to be able to have something not go right and still have the board never know it.
Gotcha. Well, it also helps too with the overhead in terms of if it gets really hot outside.
That's right.
So one of the things too, you're showing off the microchannels, right? And so then we have this device here. So it's kind of like, okay, and I think a lot of people have questions on this too. It's like, how does this actually cool with these channels, right? So I think we can kind of maybe go into that. We can, I don't know how you want to introduce it, but that was something I was just thinking of. I was like, well, people want to know that.
How about an anatomy lesson? How
Sure.
does that sound?
Let's do an anatomy lesson.
So here's the anatomy lesson. So this little device is actually like a heat sink. It has these microchannels in it. As a matter of fact, it has this many microchannels in it, just like this thing. What this piece is here, this is an aluminum vapor chamber. And in fact, if you were to cut it open, you'd see that it has a number of microchannels in it, and it has a very small quantity of acetone in it because this is made out of aluminum, and aluminum vapor chambers have acetone. Copper vapor chambers have water.
It's also known as a heat pipe too.
That's right, and it's
thermal nerds.
It's like a heat pipe. So this thing over here, that's a heat pipe. That's a vapor chamber right there. Now these are nickel plated. They're actually copper. They're nickel plated, but there's a vapor chamber and that's a heat pipe. But they're really the same thing. They work off of a two-phase system, they call it, where you have a liquid phase and a vapor phase after the liquid evaporates. And so they spread heat. This vapor spreads itself around at a very high rate of a very high speed. So that's why people use vapor chambers and heat pipes. Well, this device, as Brian said, this is a complete actually cooling system here that cools as much as this does. So this cools about 180 watts. It's an AMD SP5 socket heatsink designed for about a 180 watt CPU. This actually cools more than 180 watts, and it's substantially smaller than that.
And I would say a lot lighter too. I think this thing's about,
lighter.
I don't know, a couple pounds.
And
This is a couple ounces.
that's right. And so what you might guess is, you might say, well, you know, it's smaller and it's lighter, but is it economic? And the answer is, yeah, extremely. And I'll tell you why, just being one for candor here. These are made out of aluminum. This whole thing is made out of aluminum. Aluminum's not very expensive and it's very light. This is only a few grams.
There you go.
So basically this thing weighs maybe 50 times more than this, something like that, because it's copper and that's aluminum. So because the material cost is low and because the design is so simple and it's redundant we're able to actually provide these to the market at a low cost. So not only do you benefit from, lower operational costs, a broader climate environment that you can operate in. If you're in an inexpensive energy market, you can overclock and it's beneficial to you. And it certainly cools at least as well, better than liquid does. It also costs less.
Absolutely. And kind of interesting too, it's these heat pipes are just basically taking the heat off the contact point for the processor, pulling that heat into the larger amount of blades here, and then just air is flowing through this thing, randomly bombarding versus
versus
this system.
Our very orchestrated molecular beam of air that we create in our devices.
And to walk you guys through here, this is the vapor chamber, the heat pipe, and we're transferring heat to both sides of the blade stack, which is right back in here. And this is essentially a duct so that we're sucking air one direction, cold air comes in through here, and this is part of our exhaust plenum effectively and ties into a central exhaust plenum. So just so people can understand how this actually gets onto the ASICs and extracts the heat from the system.
So another way to look at this brown thing here, which is, by the way, a piece of molded plastic, which is also inexpensive, we refer to it as a chimney. And the reason is, cool air goes into the where the microchannels are. The air passes through the microchannels. That's how when they extract the heat from the ASICs, and then the hot air goes out the top of the chimney, just like in your home.
Yeah. And honestly, with all the guys I've been talking to, with what's going on in the ASIC world, what's going on in the basically in this microprocessor world, is it's getting hotter and more dense, and there's more heat being generated by these devices than we have ever seen in the density we've seen. And so they're starving for solutions. Right now, the main answer out there is these big water blocks. So this works better. This works better. And why do you want to bring liquid into the data center when we can do it this way? So
that's a
huge advantages.
Perfect segue. You guys are talking about the market, and this is just such a simple, elegant, effective solution, not just an energy transfer and cooling capacity, but it's cost effective too. It just seems like a complete no-brainer. What, in your experience, Scott, has been the adoption rate across different industries? Have you noticed one to move quicker? What's been your experience in people adopting this technology when it's clear that it is the best solution on the market?
Well, adoption is controlled by several factors. So, meaning that I'll give the example of the data center industry. So the data center industry has a supply chain that they buy from. And that supply chain involves, let's say, sheet metal companies that make ducting and that make, evaporation systems. And normally the big hyperscalers, they'll have 5-year contracts with those companies. And there's a whole group of people and there's a whole plan that has to come into place if you're going to actually build a data center on time. And they have a habit of building them on time, and they're put up very quickly. If you have something different, like we did a few years ago to the data center industry, they said, well, this is the best technology in the world. Congratulations, you're going to take over the whole thing someday. And the reason why it was someday is, for the time being, the supply chain couldn't be interrupted. But here's what's happened, Monica, is that over the years, because of what Brian just said, the electronics have become more power dense, and they've started to require some kind of extreme cooling, like liquid cooling. Well, now, if you have a conventionally built data center that has air conditioning systems and it has generators for power backup and it's got blowers to blow cold air around the data center and all of that, and instead now you have to put in a liquid-cooled architecture in an engineered facility, the supply chain has been absolutely ravaged by liquid cooling. So today, those hyperscalers and all data center operators, including Bitcoin operators, are going, now what do I do? If I have to use liquid, it's a completely different supply chain. The liquid cooling companies aren't scaled up, by the way. They don't have capacity to fulfill the needs of the data center market. Bitmain, by the way, to their credit, they are a mass producer of liquid cold plates. I give them credit where it's due. They at least have scale, which is good for them, but no one else really does.
Bitcoin miners are far more adaptive too, where we move at a rate that's very, very quick compared to the HPC space. I mean, I can tell you the first mainstream, there's been some hydro miners produced in the past, the S9 Hydro and some other ones and some smaller, home projects. But the first real large commercial enterprise miner that was built is the S19 Hydro. Which actually we have one of those. It's kind of what this guy is right here. It's one of the first of the Hydro models. But to give you an idea, the amount of retooling that Bitmain has done to get into this technology and the rate at which they've done, the S19 Hydro came out, I believe, in October of 2023. Somebody can fact check me on that. It was either October 2022 or 2023. But the point is, the adoption that we've seen now sitting here in 2025 is that I would say, and MicroBT, to their credit, they've ramped up hydro production as well. But I would say that in terms of new site builds, that over 50% of new sites that are being greenfield built from the ground up are going into the hydro technology. So you're looking at in a couple year to few year period, Bitcoin mining has pivoted from going from air-based miners, the shoebox style, to getting their feet wet in an immersion and then just kind of going, I don't know if I want to do the immersion thing, and then going full blow into hydro. And so we're seeing hundreds of megawatts, if not gigawatts, of hydros coming online within a very compact period of time, which is why this technology is exciting for the Bitcoin space, because we have the ability to rapidly pivot it and scale into a superior cooling. And to be honest, Bitcoin mining, SHA-256, it's the only silicon production where we're using 99% of the chip all the time, unless we're not running. Like we are not, even the AI inference and HPC, again, they're using like 30%, inferences like 80, 90%. We're at 99%, right? So we are keen on adopting innovative technology at a higher rate than a lot of the other industries are. So I think
because
that's
of need.
Because of need and demand, It's just reality, right?
Yep.
We don't mess around. We move quick, So
That's good, Brian.
Yeah.
Thanks.
So knowing that this technology is on the horizon, what do you see the equipment for Bitcoin mining looking like in the future?
Drastically different, right? So right now, you can look at some of our sites, like our McAllen site. We've got containers set up there that are spaced apart by about 80 to 100 feet apart, big blower fans on them, and we're throwing air all the way across. We've got huge distances in between the containers to prevent the hot air from recirculating into the cold air of another one, right? So these very large physical footprints of sites that take up potentially acres. So you look at a Bitcoin mining site, or you see these super tall vertically stacked buildings with racks that just go up 20, 30 feet into the air, and scissor lifts go. Right. What I foresee in terms of what this technology brings is we're going to shrink everything down. We can we're looking at, say, stick a megawatt, not in a 40-foot container, but in a 20-foot container operating off of a blower, high-efficiency blower. You've got an exhaust pipe that comes out of that blower that's maybe 8 inches around that you can stick a pipe on the top of the container, shoot it right up. And then the intake air around it, well, if you've got all your exhaust going up through effectively a chimney coming out, means I don't need a lot of clearance, right? Well, my biggest pain in the butt is probably going to be the insurance contractor saying, I need you to space these things out by at least 40 feet so that if this one somehow burns, even though it's all metal, it won't light this one on fire, which makes no sense at all to me ever. But the point is we can go very dense. Some of the calculations we've looked at, we've got a 5-acre site we're running about 10 megawatts on. So you're talking a density of about half a megawatt. Don't get me wrong, that's pretty dense, right? When it comes to electrical utilization, if anything knows how much energy a house uses, right? It's very, very dense. But I mean, we could probably stick 50 megawatts potentially on a little more than an acre at this scale.
Yeah.
So the amount of just physical infrastructure we need is less. It's more compact. It's running on a more efficient platform. So, and it's far more portable, right? You don't have to connect to dry cooler. You don't have, chemistry that you're dealing with on a daily basis or weekly basis, monthly basis at the very least, hopefully, to make sure that you're not deteriorating your water blocks themselves through that water loop. You don't have those enemies. I believe that the only technical challenge, not even technical challenge, is we just have to have a filter, right? We're just filtering the air.
That's right.
But the catch is we're filtering a lot less air
We are.
than this, right?
That's right.
So that's one thing everybody hits me on. They're like, man, we have to filter. It's like, right, but we're not saying 200,000 CFM of air on a 40-foot container with the wall wide open that we're filtering, right? We're talking,
A tenth of the quantity of air, and so your filter is going to last 10 times as long, basically. And
Right.
So, yeah, that's right. No, you're right.
Exactly. And that to me is exciting, right? The maintenance requirements go down. We pick up efficiency on the chips just in terms of reduction of the current leakage. We're able to basically keep the chips cool with hotter air, and we're able to save energy on the chips, and we're saving energy on the blowers and the axial fans. I mean, you put all this together, it's like you're running, anywhere from 15, 20% more hash rate, less power utilized, efficiency increases, maintenance issues gone. Like, to me, that's exciting, right? Like, that means I can scale quickly. I don't need access to water. I don't need access to a bunch of different things. I can be far more dense, and I don't have sound ordinance issues either.
Yeah.
This thing's going 20 decibels, 40 decibels outside of the container compared to the 80 to the 100 that I'm throwing around now with my current fan. So to me, that's really, really exciting. And that's, Monica, where I see, the future of Bitcoin mining is far more industrialized, far more scales, and, conforming to some standards for once as well. So that's kind of an exciting notion that we're looking at on the industrial side. But
Exciting's definitely the word for it. Do you have a timeline on when you see that coming to fruition?
yeah, I mean, look, there's some research and development we have to do in terms of getting these things to work the way we want it, and then kind of perfecting a standardized model, right? What we know now is this technology works, it works well, these are scalable, cost effective. Now it's time for us to build the miner to fit the technology properly, to get the boards functional, to get it done. When you're looking at what type of adoption timeline you're looking at, they've probably been developing the S19 Hydro for about a year and a half prior. We're looking at a similar time frame, but if you look at the rollout window and how quickly once you have a solution, and Scott, I think from a scale standpoint, you guys can keep up with
Oh, yeah.
the demand that we're potentially looking at as a Bitcoin miner.
Should I mention something about that?
If you want to,
So,
it's up to you.
As a CEO of a company, one of the things you have to, a company with a product, a physical product, one of the things you have to think about is the market that you're in and what its requirements are, its volume requirements are. And in the industry, terminology for that is scale. And so you have to be able to, as a hardware manufacturer, you have to be able to meet the demand that the scale of the industry has, or you're not a viable vendor. So what we've done is we've partnered with actually global manufacturers that are at global scale already. So these devices we can create and provide to our clients at many megawatts a month. And in fact, more than that, we can do hundreds of megawatts or even gigawatts in a few months. So it's important that we have our supply chain is robust enough to meet the scale of the market. Mm-hmm. And fortunately, we are.
Absolutely. And the market's pretty big, right? If we look at Bitcoin miners in general, we're talking gigawatt plus per year annual basis. And the technology is always rolling over. As the chips get better, the equipment degrades over time in terms of their performance, and then you have to replace them at these facilities. So there's a constant cycle of demand for Bitcoin miners as you're moving forward. And we've seen that adoption with the hydros. So it's exciting to see what this could do.
Seems like this is just the perfect solution, honestly, for this industry and any electronic industry. What are you most excited about, Scott, for the direction that this is going with A.R.T Digital?
Well, first of all, A.R.T Digital has experts. And we, as a company, Forced Physics, is not, we are not experts in Bitcoin mining. We are not experts in AI. We are not experts in the different disciplines of the people that use our technology. A.R.T Digital is in the unique position that they have, Brian, first of all, their depth of knowledge, their contacts around the industry, their years of experience in dealing with the different cooling technologies in particular, makes them very well versed. And in fact, I think from Brian's enthusiasm, you can see that when he sees something good, he knows it and he likes it. So I think that first of all, just the quality of the people at A.R.T Digital. Secondly, and certainly as importantly, the people at A.R.T Digital and with their contacts in the manufacturing arena of Bitcoin equipment, that design that Brian was talking about, the new designs that will come as a result of the marriage of this cooling technology with the Bitcoin boards of the future, their input on how to engineer and design those boards is very critical. The market has to say, this is something we want. And the designs that I've seen that A.R.T Digital has in mind, the higher power density is going to be very appealing to the Bitcoin miner. The lower cost and higher power density, it's just always an economic argument, and the economics are straightforward. So to me, that's very exciting. That we have the ability to meet the scale is a plus.
Absolutely. And I'm super excited too to kind of continue to work as you guys evolve this technology as well. I mean, just the innovation that I've seen out of Force Physics over the last, almost 6-7 years of me working with you guys, going from some of your earlier designs to this efficient design is kind of inspiring, right? I'm trying to remember where you were in terms of like per watt, what you were back, then versus now in terms of cooling, right? Like, I was trying to remember. I'm sure you have these numbers memorized, Scott. But what was the difference between this device here and some of your earlier devices?
So we've actually improved the energy efficiency of our technology, meaning, like Brian just said, that we remove more watts of heat per microchannel. So this has about 150 microchannels in it. Each one of them removes somewhere in a good design of ours, it removes somewhere around 1.5 to 1.8 watts. It used to be when you first met us
half a watt.
that we would do about 0.5 watt per microchannel. So we've gone 3-4 times that, and you'll see even more, Brian. Coming.
Okay, I'm excited for that, Scott. Honestly, it's incredible technology, and it's time to get it rolling out. And, I think Bitcoin mining has the best application for this compared to anything else in the industry. We have the most demand for it. I think the environmental impact of this is huge. We know that water is a challenge at our sites, taking the city water or even just the amount of water that we need for evaporative cooling. And we're doing so and it's a big challenge when you've got these desert climates, right? I know a big area that's interested, the Middle East, in Bitcoin mining, but there's so many challenges around the heat. And so, what do? Do they just throw a bunch of air conditioning and compressors at it? And now suddenly they're using 50% of the energy to just keep the Bitcoin miners cool so they can run them in that environment? Or, do they go over to hydros and then they're using a tremendous amount of desalinized water in order to cool that, which would otherwise be drinking water? And then what's the cost associated with that? So when you look at utilization for the technology, it's like what I'm most excited about is the positive environmental impact it can have for these locations that have surplus electricity, but they don't have surplus water to spare, right? Mm-hmm. And this technology can really go a long way for additional adoption, different geographical locations that have, generally been offhands are not interested in for Bitcoin mining, right? I would say we got a great sunlight out here in Arizona. We got great solar and decent energy rates at night, but I'm never going to build a Bitcoin mine out here because it's too freaking hot.
Yeah.
It's not going to operate all the time because it's over 100 degrees for 100 days out of the year.
And and you either have to run, like you say, that very expensive air conditioning, which you also need generators to back them up when the power goes down, or else your whole, operation goes down. And also, there's no water, and we don't use any water. So I guess, as Brian has just nailed it, it's no water is a good thing, and no air conditioners is a very good thing.
And water and electronics generally don't mix very well either, Scott.
No, they don't, Brian.
Another good point there.
This is a journey definitely worth following. Where can everybody listening watch this journey unfold, watch this technology just explode, and see how it works in the Bitcoin mining space?
Absolutely. You should definitely follow both of these companies. So A.R.T Digital, we're an online public company. We're CGAC. It's our symbol ticker on the OTC. You can follow us on Twitter. We're on LinkedIn as well. We'll be pushing updates on LinkedIn and Twitter, and both the companies will be obviously sharing results and data as we move forward and, showing these videos. And there's also some really interesting content that's already been produced that's out there, for our companies that I'd suggest people go take a look at and, see. It's not, this isn't a brand new technology. I mean, it's new in terms of nobody else has really utilized it, but it's not new. It's just finally coming to fruition and utilization. So please, follow us on social media, follow us on X, LinkedIn. We'll be hopefully doing this more frequently and having some additional, follow-up feedbacks as we, run this forward and get more frequent updates as we're developing. So.
And Scott, what about you? Where can we find you and your technology?
Our website is www.forcedphysics.com, and that's where you'll see our information. Also, you'll see videos on that website. There are links to videos and links to other educational materials, white papers and such. I would say for the Bitcoin space, go ahead and go to Brian's location, and he will keep you best updated.
Awesome.
Perfect.
Well, thank you so much. I'm so excited.
Thank you.
Thank you.
Brian, thank you very much.
Thank you, Scott.
You're welcome.
Appreciate it.
It's pretty good.